Euclidean geometry, proof of the proportional intercept theorem. So we'll start with a preamble. We draw a line parallel to one side of a triangle, and it is now going to divide that side and that side in proportion. That over that is equal to that over that. But before we get into the proof, let's have a look at a couple more facts about areas of triangles, because we in fact use areas of triangle in this proof. There we have two triangles sharing the same altitude. We have, in fact, three triangles, but there's triangle AQP, there's triangle BQP, there's the height of triangle AQP, and because triangle BQP has an obtuse angle at P, the height is there. Picture standing at the top of this cliff. There we are, this cliff here. And if we had to drop a stone, that's where it would fall. So that's the altitude of that triangle as well. Now the area of a triangle is half base times height. So in this triangle, we have half base, which is AP, times height QG. And in this triangle, we'll have half base, which is BP, times its height, QG. Now, you'll notice that their halves and QG is the same, so we can take them out. And we end up with the area of this triangle to that triangle is equal to the ratio. The ratio of the areas is equal to the ratio of the bases, AP over BP. And there, that fits in to, have a look again, that fits into your proportional intercept theorem. There's a shadow of the proportional intercept theorem there. Now have a look how this setup fits right into it. There, and we're going to use that in the proof of proportional intercept theorem. Our second fact, that if we draw any triangles between parallel lines, then they will have equal heights. That's fairly obvious because any perpendiculars drawn between two parallel lines must be equal in length. We won't go into the geometric proof of that, but it's pretty obvious. So let's now draw three triangles. There's a triangle here, there's a triangle here, and there's a triangle here. Now they're on the same base. So the area is equal to base times height. And that means those three areas are equal because they have the same base and the heights are the same. And we use as a reference same base, same parallels, meaning they're on the same base and they're between the same parallels. So have a look at this diagram here. We're back to the proportional intercept theorem diagram, so we take that there, and if we come down here, we have a pair of parallels, and there is a triangle, there is a triangle. So the green triangle and the mauve triangle are equal in size, equal in area, that is. And when you write triangle PBQ equals triangle QCP, that means the areas are equal. They're not congruent, they're not exactly the same shape. They are just equal in area. So we can go into the proof now. There's our diagram. Now, when you're doing a proof, any proof in Euclidean geometry, if you can show in the diagram something given, you don't have to put given in the proof. You don't have to write given and whatever the fact is. But if it cannot be shown in the diagram, then you need to write it. For example, if you have a circle where O is the center, you cannot show that O is the center. You cannot show that very easily in a diagram, so we write given O center. So we go straight into required to prove, RTP. And we are required to prove that this divides that proportionally, and required to prove in a theorem proof interprets it according to the diagram we're doing. So it's not going to write a line drawn parallel to one side divides the other two sides proportionally. It's going to write AP over PB equals AQ over QC, interpreted by the figure. Now we need a construction. You'll remember that we had those two little lines across there, so we're going to draw those in. And we also have that perpendicular height there for that side-on triangle, so we'll draw that in. Now we can do the proof. Now remember our two facts. The first, the two triangles sharing an equal height, and the second, two triangles between a pair of parallels. So we're going to use the first. Triangle ABP, triangle APQ, triangle APQ and triangle PBQ. There's the diagram, those two triangles, equal half AP times QG, and this one is half PB times QG. The halves cancel, the QG's cancel, and we end up with this triangle APQ over triangle PBQ equaling AP over PB. This triangle here over this triangle here equals that side over that side because they have the same height. Now in geometry we have a very nice way of going about things where if we now have exactly the same proof in a different situation in the diagram, we can write similarly, and then being lazy mathematicians we abbreviate that to the word simile. So I'm going to say similarly that triangle over that triangle equals that side over that side. There it is. Same reasoning, exactly. But now we're arguing, so we say, but if you have a look at this, that and that, APQ is common, and PBQ equals CQP. Have a look. PBQ equals CQP. There's the setup there that we had earlier, the green and the mauve triangles. They're equal because of same base, same parallels. So we have that common, and that is equal to that, which means this bit is equal to that bit, which means that equals that. And there is our proof. But of course, being mathematicians, we can always complicate things. So I'm going to go back to the preamble. I'm going to say the dividing line does not need to be through the triangle, inside the triangle. So there are triangles, but two of them I'm going to draw the line outside. So there we are. Instead of saying it divides the other two sides proportionally, it says it divides the other two sides produced if necessary proportionally. So have a look. We're going to put this line there. Notice we're going to take that line, and instead of being between the two ends of the triangle, we're going to put it down below. And this one, we're going to take that and put it above. This looks terribly complicated, but in fact, in the end, we're going to do exactly the same proof as the one we've done. There we are. AP over PB equals AQ over QC. Notice the way it goes with the other triangles. So let's do the second proof. Required to prove. And that's pretty straightforward. Now, what we have to make sure is that our construction follows exactly the same path in these two figures as in that one. Then we can ignore these two. Construction. Join BQ and CP. Have a look. I've joined BQ and CP. So there's BQ, there's CP, there's BQ, CP. Looks a bit strange here, but just do it because it's going to follow exactly in the proof then. We draw the perpendicular from there, so there it is. So we draw from Q to AB or AB produced, and Q to AB or AB produced. There it is there. Have a look at that briefly and see that it's exactly the same thing in both. We're drawing a perpendicular from Q to the solid line. Now, we can ignore the extra two diagrams and just do our usual proof just looking at this diagram. Now, if you want to, try following it through. Try pausing and following it through on these two diagrams, and you'll see that it is exactly the same thing. And that's your proof done.